Hello everyone, welcome to this 10th lecture of States of Matter, Gases and Liquids. Myself Varad, I'm a doctoral student at the Department of Chemical Engineering, IIT Kanpur. So in the previous classes, we have seen that the real gases deviate from ideality, and we have also quantified this ideality in terms of a quantification factor, which we called a compressibility factor. We studied that this compressibility factor can be greater than 1 and can also be less than 1. Then we have also studied the when it is less than 1, what happens, and when it is greater than 1, what is the conditions. Further, we also established that this is compressibility factor. In reality, is nothing but the ratio of real volume to the ideal volume. And then at the end of the class, we also studied the deviations, causes of deviation from ideal behavior, causes of deviation of real gases from ideal behavior. We mainly pinpointed these to two assumptions which were wrongly assumed in kinetic theory of gases, which was the kinetic theory of gases assume that the volume occupied by the molecule of gas is negligible as compared to the total volume of the gas. We studied this. We understood why this is impossible and what was the issue with this thing. And then the second reason was that there is no interactive forces between the atoms of the gases. We also studied and justified why this assumption is false. And then in this class, what we are going to study is we are going to study the corrections which were proposed by Van der Waals and which gave rise to the new equation of state, that is the Van der Waals equation of state. It's also called as a cubic equation of state, right? So first, let us write this down. So lecture 10, states of matter. The first topic which we are going to study is correction of corrections of deviations, which is nothing but Van der Waals equation of state for real gases. Van der Waals equation of state for real gases. Okay. So to account for the behavior of real gases, it becomes necessary to apply suitable corrections to the ideal gas equations, right? So ideal gas equation is PVM is equals to RT. Right? This is the ideal gas equation. Ideal gas equation. So we have to apply some corrections to it. So we apply some corrections, which gives us a function of P VMT equal to 0. This is real gas equation, real gas equation of state. Okay, or we also called it as Van der Waals equation of state, right? So US stands for equation of state, equation of state. Okay. So as to make it applicable to the real gases, the ideal gas equation was modified by Van der Waals, who incorporated the idea of finite molecular volume and intermolecular forces. The modified equation of state, which explains the deviation of real gases from ideality, is known as Van der Waals equation of state. Right. So let us write this down. Right. Van der Waals modified the ideal gas equation to account for finite volume, finite molecular volume, finite molecular volume, and intermolecular forces, molecular forces. Right. So the first term which we introduced was the Van der Waals applied. Van der Waals applied following following corrections to the ideal gas equation. Corrections to the ideal gas equation. The first one was corrections due to volume. Corrections due to volume. Right. Corrections due to volume. So in this, the volume occupied by the molecules cannot be neglected in comparison to the total volume. This means that the molecule are not free to move in whole volume V, but the free volume is less than the observed volume. In other words, volume of the gas is less than the observed volume, right? So, so the big key point is that the volume occupied by the molecules, the volume occupied by the molecules cannot be neglected in comparison to total volume, in comparison to the total volume, right? In other words, what we can say is, in other words, the ideal volume of gas is ideal volume of gas is less than the observed value, less than the observed value, right? It was therefore suggested by van der Waals that the suitable correction term may be subtracted from the observed volume. The correction term from 1 mole of gas is called as B, and B is a constant depending upon the nature of the gas, right? So let us write this down. It was therefore suggested by, it was therefore suggested by van der Waals, suggested by van der Waals that a suitable correction term, correction term may be subtracted from the observed volume, from the observed volume, right? And this correction term was, this correction term was denoted as B and called as excluded volume, excluded volume or co-volume, and this, and the value of this depended on the nature of gas, and the value of B depends upon the nature of gases under consideration, right? Thus what we can say is, thus if V be the volume occupied by, volume occupied by 1 mole of the gas, then the volume available, volume available to the molecules for the movement, the molecules for the movement, that is corrected volume is, corrected volume is V corrected is nothing but V minus V for 1 mole, right? For n moles of gas is said, for n moles V corrected becomes V minus NB, right? This means that instead of moving in volume V, the molecules are now moving in a volume V minus NB. It may be noted that B is not equal to the actual volume of the molecule, but it has been calculated to be 4 times the actual volume of molecules, right? So it must be noted that, must be noted that B is not equal to, not equal to actual volume, actual volume of the molecules, but it has been calculated to be 4 times the actual volume of the molecule, actual volume of the molecules, right? So if molecules are assumed to be sphered having a radius r, then the volume of one molecule, so let us write this down. If the molecules are assumed to be spheres having radius r, having radius r, then the volume of one molecule of gas is nothing but the volume of the sphere. Then the volume of one molecule of gas is equal to 4 by 3 pi r2, right? Therefore, the excluded volume, which is nothing but B, which is nothing but 4 times volume of one molecule becomes 4 into 4 by 3 pi r cube, right? This is for one molecule, right? For n moles, it becomes, for n moles, P is becomes 4 into 4 by 3 pi r cube multiplied by Avogadro number, right? And this is very important, right? So extruded volume of the extruded volume is 4 times the actual volume of the molecule. So this statement, let us try to understand this statement. Here you see, let us assume that the molecules are spherical with a radius equal to r, right? So let us assume that these are the molecules. This is molecule 1, this is molecule 2, this is molecule 1, this is molecule 2, each having a radius of r, right? Then the volume of this molecule is going to be how much? Volume of one molecule is 4 by 3 pi r cube, right? As is clear from the figure, the distance of closest approach of two molecules is 2r, right? So this is the maximum distance they can approach, right? And this distance corresponds to 2r, right? This distance corresponds to 2r, right? Thus, if we consider only bimolecular collisions, then the volume occupied by a sphere of radius 2r represents the excluded volume per pair of the molecule, right? So hence what we can write is, we can write that excluded volume, let us write this here, excluded volume per pair of molecules, per pair of molecules, it's going to be equal to 4 by 3 pi, because the distance of collision is 2r, here it's going to be 2r, right? Which corresponds to how much, right? So this is for pair of molecules, right? So for one molecule, it's going to be half. So it's 1 by 2 multiplied by 4 by 3 pi 2r cube, which when we solve comes out to be 4 multiplied by 4 by 3 pi r cube, right? Therefore B corresponds to 4 into 4 by 3 pi r cube, right? Which is nothing but volume occupied by a single molecule, right? Now the next is the correction to intermolecular forces, right? The second is correction to intermolecular forces. Right? So as discussed earlier, some attractive forces exist between the molecules of the real gases, right? Let us try to understand this with the help of an image. So see, so we have right here. So consider this system. So here what we have is, we have a molecule. So the right hand side molecule, this molecule is present in the bulk of the system, in which this molecule is being attracted or repulsed, or the forces acting between them in all the direction is uniform. Whereas for the surface molecule, which is at the surface, at the interface, has different forces acting on it, right? So molecule, this is molecule near the wall, hence it has a net inward forces, right? Whereas molecule in the middle has no net force, right? So as discussed earlier, some attractive forces exist between the molecules of the real gas, right? So consider this figure, a molecule of gas in the middle of the container. This one, the molecule is being attracted uniformly by the neighboring molecules. The attractive forces neutralize one another, and there is a resultant pull on the molecule. On the other hand, when the molecule approaches the wall of the container, it experiences an inward pull, and as a result of attractive forces exerted by the neighboring molecules inside the vessel. Thus, the molecule strikes the wall with less force, right, than it would have done if there were no attractive forces. Therefore, the absorbed pressure is less than the ideal pressure, right? Hence, we can conclude that observed pressure is less than actual pressure. Hence, we should add a correction term to it, right? Hence, what we have is P corrected has to be P of ideal gas plus some P dash. Now, all if somehow we are able to find this P dash, we can find the actual pressure, right? So this is the observed pressure. This is the observed pressure, and this is the additional part. So Vanderbilt suggested that to correct the pressure, a pressure term equal to A by V square for 1 mole and A by N square by V square for N mole is is to be added, right? So van der Waals suggested that P dash has to be equal to a n square by v square, right? Where n is the number of moles, right? Therefore, as per him, P corrected has to be P actual plus a n square by v square, right? For n moles, right? So hence, if we substitute this correction term in the ideal gas equation, also the pressure term, which was this one, right, into the ideal gas equation, we should be able to figure it out, right? The equation, the resultant equation which we will obtain has to be equal to the actual term, right? So here what we write is P corrected is nothing but equal to P plus P dash, right? Where P dash is nothing but a n square by v square, right? Hence, the van der Waals equation of state is van der Waals equation of state. So before that, let us write the ideal gas equation. So ideal gas equation is what? Ideal gas equation is nothing but PVM by RT, or PV is equals to nRT, right? So if instead of this we write P dash V dash, which we got from van der Waals correction, van der Waals, right, and nRT, then this becomes the real gas equation. Real gas equation, right? Real gas equation, right? So as per van der Waals, we already saw that this P dash has to be nothing but P plus a n square by v square, and this V dash has to be V minus NB. Therefore, what we get is P plus a n square by V square multiplied by P minus NB is equal to nRT, and this is what is going to be the van der Waals equation. This is van der Waals equation of state, right? For 1 mole, this equation corresponds to P plus A by V square into V minus B is equals to RT. Right? So this is very important equation. If you can see, if you take on the both, multiply both the sides by V square, what we get a cubic equation of state, right? Hence this is also called as a cubic equation of state, right? So where this A, which we saw here, is nothing but a constant, A equal to constant, which depends on nature of gas, nature of gas under consideration. Okay? So now let us look at the significance of this A and B, right? The next topic is significance and units of A and B. A and B, right? The constant A and B are called as van der Waals constant, and their value depends on the nature of gas. This A and B, these are called as van der Waals constant, and their value depends on the nature of gas under consideration, right? So let us first see the van der Waals constant A. Van der Waals constant A. The constant A measures the forces of attraction between the molecules of the gas. So A, this measures the forces of attraction between the molecules of a gas. Greater the value of A, greater is the strength of van der Waals interaction. Greater the value of A, greater the strength of greater the strength of van der Waals interaction. Strength of interaction between the molecules. Interactions between the molecules of a gas, right? As expected, the value of A for gas with lower molecular weight, such as H2 and N2, is quite low, whereas value of A for higher molecular weight is relatively high, right? So A is higher for the value of A is high, is quite low. So as expected, the value of A for the gas with lower molecular weight is quite low. So A is low if molecular weight is low, A is high if molecular weight is high, right? It may be noted that the greater value of A also reflects the greater tendency to be liquefied, right? Higher the A, higher the value of A, value of A, greater the tendency to liquefy, greater the tendency to liquefy, right? Therefore, gases having higher value of A will also be highly liquefiable, right? And its unit can be found from this, that P dash is nothing but A n square by V square, where this is in nothing but SI unit will be pascals, right? Its unit will be mole square, and its unit will be liter square or meter cube, meter to the power 6, right? Therefore, what we can write, A is nothing but P dash V square by N square, which is nothing but pressure into volume square divided by mole square, right? Therefore, A unit of A comes out to be atm liter square by mole square, or A corresponds to bar decimeter to the power 6 divided by mole square, right? So now let us understand about the van der Waals constant B. Van der Waals constant, van der Waals constant B, right? The constant B relates to incompressible volume of the molecules and measures the effective size of the gas molecule, right? So B relates to the incompressible, relates to incompressible incompressible volume of the molecules, volume of the molecules, right? And measures the effective size, and measures the effective size of the gas molecule, right? It may be noted B is not equal to actual volume of the molecule, but is 4 times the volume of the gas, 4 times the actual volume of molecules, right? So we know that V dash is nothing but NB, which implies B is equal to nothing but V dash by N, which is nothing but volume by moles, which corresponds to liter by mole, or decimeter cube by mole, right? This is very important, right? So now let us look at the applicability of van der Waals equation. Applicability of van der Waals equation, right? So van der Waals equation is P plus an square by v square multiplied by v minus nb is equals to RT. For 1 mole, this equation changes to 1 plus a by v square into v minus v is equals to RT, right? So let's consider at low pressure. At low pressure, V is very greater than B, right? Hence, we can assume that B is very less than V, right? Hence, we can neglect P, right? Hence, the term then becomes what? Hence, we can write that this equation, this expression changes to like this: P plus A by V square into V. This implies V minus B is nothing but V. We can approximate it. Is nothing but RT, right? Hence, what we get is PV square plus A by V square multiplied by V is equals to RT, right? PV square plus A by V is nothing but RT, right? Hence, what we say is PV square plus A by VRT is nothing but 1. Then we change PV square by VRT plus A by VRT is nothing but 1, right? Hence, we can say that PV by RT plus A by VRT is nothing but 1. Further changing, we get PV by RT is equals to 1 minus A by VRT, right? That's what we can say. At low pressure, PV by RT, that is Z, is less than 1, right? What does this mean is PV by RT is what? Z is equals to 1 minus A by VRT. So Z is equals to 1 minus some positive quantity, right? Therefore, at low pressure, Z is less than 1, right? Why? Because Z is nothing but Z is equals to 1 minus A by VRT, right? You can also say that Z decreases with increasing pressure, right? Now let us understand about at high pressure, right? So the equation for 1 mole we have is A by V square is equals to RT. Sorry, multiplied by V minus B is equals to RT. This is nothing but Van der Waals equation. So at high pressure, what we can say is at high pressure V is very small, so that B cannot be neglected in comparison to V. But A by V square may be considered negligible, may be considered negligible to P. Therefore, A plus P by A by V square, this becomes equal to P. Therefore, what we can write is P into V minus B is nothing but RT, right? Which means PV minus PB is equals to RT. Dividing both the sides by RT, we get minus PV by RT is nothing but 1. Therefore, PV by RT is nothing but 1 plus PV by RT. This is nothing but Z is equals to 1 plus PV by RT, right? This implies Z is equals to 1 plus some positive quantity, right? Hence, at high pressure, Z is greater than 1, right? Now let us move on to the third, which is at high pressure, at high temperature, and low pressure. So if T is very high, then volume is also very large, right? Hence, therefore, V minus NB can be written as V. Also, A by V square can also be neglected, right? Because as pressure is very low, right? Therefore, P plus A by V square corresponds to P. Therefore, Van der Waals equation of state, therefore, P plus A by V square into V minus B is equals to RT. This equation transforms to P into V is nothing but RT, which is ideal gas equation, right? Therefore, at high temperature and low pressure, real gases behaves like ideal gases, right? Now let us try to understand the differences between these two types of gases. So here we have ideal gas and here we have real gas. The first point is ideal gases obey all gas laws under all conditions of temperature and pressure, whereas real gases obeys gas laws only under low pressure and high temperature. So ideal gas obeys all gas laws under all conditions of temperature and pressure, whereas real gases obey gas laws only at low pressure and high temperature. Hmm. Second point is in ideal gas, the volume occupied by the molecule is negligible, whereas in real gas, the volume occupied by the molecule is not negligible as compared to the total volume occupied by gas. In ideal gas, the volume occupied by the molecules is negligible, whereas in real gases, the volume occupied by the volume occupied by the molecules is not negligible. Right. Third point is the forces of attraction among the molecules of the gas are negligible, whereas the forces of attraction among molecules for real gas are not negligible at all temperatures and pressure. Right. The forces of attraction among the molecules of the gas, molecules of ideal gas are negligible, whereas the forces of attraction between molecules of real gases are not negligible at all temperatures and pressure. At all temperature and pressures. Right? And the fourth one is the ideal gas obeys this expression PV is equals to nRT, whereas the real gases obeys Van der Waals equation, which is AN square by V square into V minus NB is equals to nRT. So with this, we have completed the expression or derivation for the ideal gas for the real gas equation. So in this class, what we have seen is we have seen the necessity for the ideal gas necessity for the development of the Van der Waals equation, the limitations of the kinetic theory of gases, and the corrections applied to this kinetic theory of gases, which gave rise to Van der Waals equation of state. We have derived the expressions for the two constants which were proposed by Van der Waals, which are respectively A and B. We have studied its unit, and we have also seen that these depend on the nature of gas under consideration. Further, we have also seen the differences between the ideal gas and real gas. And at the end, we have also studied the limiting conditions of this Van der Waals equation of state at low pressure, high pressure, and at high temperature and low pressure, and how this expression simplifies. Right. So in the next class, we are going to study about the liquefaction of gases and the critical phenomena. So we are going to study about the critical points, that is the critical temperature, critical pressure, and critical volume. Further, we will also try to find the this critical constant using the in terms of the constant which were proposed by Van der Waals. And then further, we will start with the liquid state of matter, and we'll study the properties of the liquid. Right. So thank you all for attending this class, and I hope to see you all again in the next class. Thank you.